report. Okay. So the first step is always data preparation. And so I have some code here. So let me take that code out here. So it's a very special data set. Make moons. Let's see. So we have to download this. So let's build this data set. So it's starting to run. And so we'll create a demo data set. Okay. Torch is not defined, so import torch. Okay. So what essentially we did that we have x comma y. So if you print x dot ship and print y dot ship, you will see there are 1,000 data points and there are two inputs. Okay. So there are two like dimensions, 1,000 data point and dimensions. So let me ask ChatGPT to help me plot it. Help me plot this. So I want to show you how I use ChatGPT. Okay. I don't want it to plot it. I just want to. So you have to take download this matplotlib. So in the libraries, and we want to plot it. So you can see it looks like this. Okay. So this is the how the entire data set looks like. So we want to build a neural network that helps us find the decision boundary, which will be kind of around here. Okay. That's the basic idea. So this is the data set. So this is the understanding and plotting the data set. So, okay. So I think we have it in a wrong place. So what we'll do here is that we'll have a markdown and we'll put it above called importing libraries. So this is a dataset preparation. So this is the basic dataset. So you change it into now x comma y tensors, torch.tensors, torch, which is very important for using neural networks. That's how torch. So every element of PyTorch is the tensor. So and based on the tensor, we can do the gradients update. Okay. So after this, the next part is to build the training data set. So build the training data set. That this is like, you can say step 1.1 or plotting the data set. Okay. Here you can say build the data set into train and test, train, val, and test, or divide the data set. So what we will do, we will use the torch utils because already is it in torch. So we'll use this torch utils to randomly split, and it's simple basic code. We can all get it from ChatGPT. That's not a problem at all. So we will first use our torch. We will build a torch data set like this, and then we will split it into 60, 20, and 20 splits like this. Okay, so you can see there are 1,000 samples here. So it is divided into 600, 400, 200, and 200. So what we did here, understand? So so this is 60% of the total length of the data set, 1,000. We are choosing 60%. This is the training size. That is, we are saying that this is equal to 600. We are saying that. We are saying that this is equal to 200. We are saying that naturally this is equal to rest 200. 1,000 minus 600, so it will be 200. Now what we are doing is that we are taking the entire data set, we are using the random split into these three sizes. Okay. And it's generating the manual generator based on which the entire randomness happens. So this data set is now divided into this three, trained data set and this trained data set, which is important for Torch. So we divide this data set into three Torch data sets. And you can see there are those many samples out there. Okay. All good, guys? All good? Can you give a thumbs up? So now we will learn how to get an output, This is important from this data set. So if you check it out, so it's taking some time. Yeah. So we want to get this output. And you can see it's a sample. So you can see it looks like this, something like this. It's a point and it's labeled as this. So the trained dataset output is always of this x comma y format. Ideally, we also use data set. So let's try to build our data set from scratch. So we'll use ChatGPT again. So can you build a data set from scratch instead of this using the moon data set? It will show you how to do that. No. Okay. Make moons, but output using dataset generator. Yeah, exactly. We will use a custom PyTorch dataset. So this is important because it's important to know. So because you have in the future you have to do like that. Yes. So here's a moon dataset, how it's prepared. So this is how you do it. So X and Y, you change it into Torch, and then understand this very carefully. I'm doing it for a specific reason. So this is how you build a general class dataset class. So it's a moon dataset. Take X and Y, and you get the X, get the Y, and then you have a length function. So essentially, this function helps you to understand that this is the total length of the dataset. So when you say print length, essentially it's calling this function. And now get item is for each of this function element, it's taking an ID and running its function elements a list of dataset. It's x1, x2, xn. So essentially it's list. This is telling you this is the list. And now what this does is this captures from that list. So this is just the length, understand this. But now it captures from the list or make a list kind of. So which is the first element, x is itself a list, right? X is itself a list, Y is itself a list. If it's not in a list, inside this you have to make it into a list. And then the get item should call those lists one by one. So essentially it's X comma Y, which you have got it here only. Like this. So this data set is tensor data set is nothing but taking those and changing into this. Here it is first changing into tensor and then using this tensor data set. Here it is directly it's making a core dataset class that is very important. All of you understood this, guys? All good, Rivan, Jadan, Anushka, Arav? Can you give a thumbs up?
Yeah.
So now we have to initialize this moon dataset. Okay, so we have not run it. So we initialize this, and now we will be able to. Now we have to divide the train tests. It's the same way. You can do it in exactly the same way. I'm just showing you it's giving the same thing. So here we are using a tensor dataset built in, but here we are using a dataset. It gives you more uh, control over how you build a dataset. Let's say now instead of this dataset, you want to build something like this. You want to build something different. So you can have total control over it here. Okay. Let's say you want to give x squared also output like this. Okay. So I mean, let's say you can define self dot x square torch dot this x to the power 2, and you can actually do idx, and you can see what happens. So now if you check it out, how to get an element from this data set, you can just do this just like it was done before here. You will see this will give an error because it expects 3 values. So xxq. Now you will see it gives right. So you will see that x is this. Now you can also print this. X. Yeah, you see it takes the square of it. So you have total control over it, which will be hard to do it here. You have to do it like you can do anything else. That's why this class is so important. So let's remove this as of now. Hmm. What is the issue here? Okay, let's try from the beginning. Okay. 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 So this is the entire, getting used to the data set. First step, data preparation. So next step is to build the model. So let's yes. So let's so we are making all this small so that we have space. So we will now do model definition. In the model definition, we first build. So we already done it last day. So we are not doing that thing again, how to build a model, but you will see that how it's almost the same. So I'm copying it here. So remember, we actually in the last class we built it from scratch, but here these are all PyTorch based. So here, so let me do one thing. Let me import all the libraries. Yes. So now what we will do is we will define this MLP. So we define this MLP here. Observe this. So here the hidden sizes are this. Remember we did it like this. Output size is 2. So dropout is what? Dropout is one specific way to make sure that it's, so we can keep dropout, we can remove dropout, but essentially it's randomly removing neurons, okay, while training. So it's kind of a regularization, just like we said yesterday. It makes the whole uh, optimization, the loss curve very smooth, so that it's easy to find the optimum. And you can see that for the hidden sizes, it builds this linear layer from previous to hidden, and then a ReLU, and then another dropout, and then a linear layer again, you can see. And then it's a depth forward. So exactly like we have done last time. Exactly like we have done last time. So we define the class. So one important thing before you do is you check out that how you check out whether, so often when you will do research, you will see that you have to build these models from scratch. So you should check out what is the output of this xn. So you already this x and y. So already this x over here, okay, this x tensor. So you will see, let's try to do it. So let's say model is equal to MLP, and input size 2. So let's keep it as it is, because yeah. So you can say hidden size is output size 2, because of the you are doing a classification. So you can make it different also, like 10 and 12. Okay, and then you see that y hat is equal to model of x. And what is the print y hat? You can see y hat is this. And you can see the gradient function is updated. That's the beauty of this. So what if you take, let's say, the entire train. Just give me a minute. So yeah. So let's say you take this. So print x dot shape. You will not get it. So what if you take x is equal to, let's say, from the first 4. So you can say you get 4 vectors of dimension 2. Like, so now you see what happens here. So you can see that you get 4 of them. Okay? If you do dot shape, you will get output is also 2. So input and output. So did you understand? So we have two probabilities, one for 0, one for 1. The output, the classification. That's why output size is 2. Make sense, guys? So we can do multiple size. So that's how the batch size is useful. So we can do multiple size. So this data set essentially makes it into a list, which is easy to. So you can see it makes it into a list, which is easy to capture. So this model can not just pass through one, but can multiple layers, multiple input data. Okay. Now the turn is for training and validation. So what we'll do is this. Yes. So let me copy and paste the function. Train model. Yes. So it's training and validation. So we have defined it. Now let's try to train it. So let's understand what's happening. So it's taking the model. Here the model is, we have already defined the model. The training data loader. The train loader is, we have defined it here. The loader is nothing but it changes into the batch size. If you remember my notes from last day, so let me show you. So if you go here and just give me a minute, it's a bit slow. Uh, yeah. So let's take this to. So if you observe, you got this data set. So the data set has this length, get item, other functions, and from that you get this data tensors. And what data loader does is this changes the data set into this batch sizes. Remember, batch sizes was very important for optimal gradients. So this is what it does. This data loader changes the entire data into this batch size batches, breaks up into batches. Okay, that is very so essentially it does this. It breaks the entire data set into batches. That's what the data loader's work is. Okay, all of you understood this, guys? So now observe this very carefully. So it takes the train loader and val loader. The criteria is the loss function. The optimizer is how you optimize it. And the number of epochs is how many epochs you will run. Patience is, I will tell you what this is. Yeah, I have not kept any scheduler or something. Lambda is the loss. I will tell you, it's a hyperparameter. So you see for each epoch, you run the number of epochs for the range. You start to train the model. You start the epoch train loss to be 0. Now you take the batch X and batch Y. So you take the train loader. As I said, the data loader outputs what? Oh, sorry. Again, let me start because it was not visible. So for we start take the epoch. We take in the range of epochs, which is 200 here. We can make it 100. And the epoch train loss we start at 0. Then we start the train loader. The train loader contains the two batches, batch X and batch Y. Okay, because output of each train loader is a batch of X and batch of Y. Like here the output is X comma Y. The train data set is nothing. So train data loader is nothing but dividing this train data sets into this smaller lists, and we get the X comma Y. And then if you remember, we did optimizer underscore 0, we remove the gradients from all of the tensors. Then we output the model, that is a y hat, and then we do the loss function criteria from the y hat and the actual y's. So we add a regularization term. The weight decay, we can actually also add it directly from here, the criterion. And we do loss dot backward that updates the gradients, and optimizer step updates the weights. And then we update the loss because it was 0, now the loss is added. And after all the batches are done, we want to divide the entire loss divided by the batches, the train leader for each data set, so that we have, so this lot item is has loss for the entire data load, like each of the batches, and then we divide over all the batch elements, and then we update the loss. We append it because we want to print it. Why we want to append it? Because we want to check the previous, keep a track of the previous one. Similarly, for model.eval, we have the validation loss. Similarly, we have the batch output, but here there is no grad. That means no gradient will be updated here. And we have the y hat, we have the loss, same exact. And then we calculate the accuracy. Let's not go into the details of it. You can understand the mathematics of that later on. And then you have the average val loss again, and then the accuracy again, and then we append it. Now comes the earliest topic, that if the average val loss is, so let's say there is a best val loss, so you can see the best val loss is kept as infinity. If there's an average, so we want the validation loss to be lower. So if the average val loss is less than the current val loss, best val loss, then the current average val loss is the best val loss. So you update the current base val loss as the average val loss. And then you update the model state also. That means This is the current best model. So patience counter is, so as I said, if you remember early stopping, the train loss will always decrease, but the validation loss will keep on increasing. Okay, it will keep on increasing, and it will keep on increase as it keeps on increasing. After a certain point, we have to make sure, like, we cannot really understand that okay, this is starting to increase now. We have to wait for a certain time and then understand okay, this is actually increasing. So for that, it's patience. So patience counter is saying that how much, for how many steps the val loss has consistently increased. Okay, if it's patience is 10, that means for 10 steps it's consistently increased. That means that the model is actually becoming bad in validation. So stop the training right now, break, and then the model is automatically saved, because the best model is automatically saved. And then if the best model is saved, we return the model, the train losses, and the validation accuracies. Make sense, guys? Arav, Anushka?
Yep.
Okay. So let's now use the train and loader and let's try to implement it. So now let's criteria is not defined. Okay, let's define the criteria. Optimized results. So different optimizers and criterion exist. Okay, let me use ChatGPT to just generate. Can you just generate code for one for implementation of this function? Okay. So actually it's generating the code, as you can see. So it's logging. Just give me a minute. So let's see. We have this. So LR is not defined. Oh, LR is okay. One. Okay. So you can see it runs the epochs now. And you can see the validation accuracy increases. And it keeps on decreasing. So it has not trained it fully right now. So let's do it for 600 epochs. So it's early stopping, it says that it reaches the best accuracy by that point. Oh, nice. By 10th. Oh. You know why it's working like this? Can someone tell me why it's suddenly returning so early? Yes. Can someone tell me?
Because part of it was already calculated.
Sorry?
Part of it was already calculated.
Exactly, because if you remember that we are outputting the model, the best model out here. That's why it's not training again like so well. So we have to redefine the model from here. So ideally you should do like this. For 600, you can see after a certain point of time, yeah, it's still decreasing. So okay, so it already stopped at 237 because it's kept on in, like it's less than, you see that at 18 1686 it's still less. Uh, or it's kept on increasing. Wait, let me see. What is the Westphal loss? Okay, so yeah, we actually do not see, we see every 10 epochs. So probably, yeah. So we are not seeing every epoch. Okay. So if we do not see, if you want to see every epoch, probably you have to remove this statement and change it. So you can see every epoch now. Okay. Okay. So you can probably see here that it's, yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 4. Yeah, so you can see here it's 47, but the next one, 1, 2, 3, 4, 5, 6, 7, 8, 9, all this better, more than this. So it's 1540. So it stops there, right? So, but you can increase the patience. You can increase the patience to be 50, and it can train longer. Now it stops here. Makes sense, guys? Although I think I didn't do it properly because I didn't run this whole thing again. But it still chooses the best one. But let's say it's, let's see, to make it easier. Let's see. So these experimentations are more important. So let's say you make the patients 100. You wait for 100 epochs to see the best one. Yeah. So you see the 100 epochs till 100 epochs that whether it's increasing or not. Yeah. So it's, you can see validation accuracy keeps on increasing as you go. So the idea is that as it becomes better, the train loss becomes less and the validation loss also becomes less. Okay. That's your general idea. Okay. Great. So all of you understood this, guys? Yes or no? All good? Jaren, Anushka, Arav. Okay.
Yep.
Okay. So one thing I would like to show you is this. What if there was uh, no patience? Okay. So we can run it for 1,000 epochs, or let's say 2,000 epochs. And let's see what happens. In this case, the thing is that it can become better with time, but it can converge, but it may not be true always. because the loss function may be really, really regularized. It's smoother, so that's why probably it is not so hard. It has probably converged by then to a proper point. Yeah, you can see the loss is also not, the training loss is also not changing. That means it has probably learned everything out there that is possible. Training is also not changing much. It's kind of converged equally on training and test. But this is for a very specific data set. Unlike in high dimensions, always easy to overfit. Yeah, you can see it's not working here. But let's take another interesting tick. Let's make this small and see what happens. So I'll make the learning rate, the step size large, okay, so that it doesn't converge. So let's see what happens now. This is now early stopping now. So you can see since it's large, it is not like it's not going to the optimum. It's like bouncing here and there, back and forth. That's why it's so low. Yeah. Okay. So you can see that this hyperparameters really matter a lot. You can see it didn't converge well. And as you will see with smaller ones, if you make it smaller, it will converge really better now, not well. But again, if you make it too smaller, then it will be bad. You can see it becomes oh I haha. No, no, no. There's a problem here because I have to run this entire thing again now because it's 99% in the first go is bad. Oh wow. It's first go it's 99%. You can see how. So this LR is the best. So this is how you do the hyperparameter tuning. So what you do is that you have a for loop over all the hyperparameters that you want. The LR is equal to this, a list, and then you find the hyperparameter for which the validation is the accuracy or whatever, loss is the smallest. Accuracy is the largest and loss is the smallest. You can see it is becoming better validation. You have never got 0.08 validation loss before, right? So this is the best LR. Did you guys understand, guys, what I'm saying? Yeah. You can see that from here it's still increasing. Although the accuracy is not like it's not changing, but yeah. So let's explore the decision boundary. Okay, final model. is axis? Okay. Wait. Hmm. We are doing a test data set now. Yeah. So you can see this is the decision boundary, right? Now, let's say you increase this lambda 1, or let's say 2. Okay. And let's see how the model trains now. It's doing 52% accuracy. So bad. It's random. So let's not do so many times. Let's just do 500 for time sake. We have to. It's 42%, very bad. It's very bad. Yeah, it's strained. Now let's see the model, the decision boundary. The decision boundary is no, it's like everything out there. Okay. So you see the hyperparameters make sense. So let's make it a bit smaller. Yes, Vivan.
Oh, wait, so I forgot what exactly is the decision boundary?
Decision boundary is the boundary. Okay, so boundary or based on which. So essentially, it's like x and y are two. Essentially, you think geometrically, if there are two clusters, let's say there is a space of dogs and space of um, cats, and decision boundary is kind of building that space on one side, which is cat, on one side it is dog. Okay,
Okay.
so even if it's in a higher dimensional space, but that's the idea of decision boundary. Okay, so let's do. Still, it's bad. So let's make it even smaller. Now probably it will be better. Still, it's bad. It's random. It cannot just find because probably the minimum has changed. It becomes too smooth that the loss minimum has been removed. Yes. Let's see if it works now. Yeah, now it becomes better. So we have 0.05 and now we have reduced to 0.01. So let's now experiment a bit between that. Let's say how about 0.1? What happens then? Let's see that. Right? This is the experiment you should do. So ideally you should do this experiment for, okay, so now it's 85%. So it's really fun to see that how the decision boundary has changed. Okay, you can see it's become so smoother. It's like the decision boundary has become very smoother, right? The loss has become essentially yeah, decision boundary is also a reflection of the loss. That means the loss is not so optimum, it's a local optimum, not a global optimum. Okay, if it increases a bit, let's say 0.01 it was, so instead of 0.01, let's say 0.07. It'll be a bit better now. Not better, but yeah. The idea is that it becomes so smoother that it's not being able to capture that complex linear relationship on nonlinear relationships. Yes. So we have to make it still smaller. About 0.03. Still it doesn't work. So you see that optimum point is very important. But yeah, it's become a bit better though. I hope it is 90. Yeah, it still doesn't reach 90. Yeah. Yeah, it has changed a bit. Started to become non-linear. So okay, so you see it started to become 90%, 90%. If I just reduced a bit, that is a sweet spot. But it's still not 99% that it was giving us. And you will probably see it's a big, yeah, you can see it started to learn this slowly, but it's smoother. Now, if there was no such thing, then let's see what happens. Yeah, it's still not 99% though. It's still 98. It's less here. You see, it's like this. So does this add any value out here? Let's see. 0.01. So it's 95.8, 98.5, 98.5. Let it reach 99, 98.5, 99. Very good. Although the loss is not the same. Loss is decreased if you see increased. It's like, why did I do it? Okay. Yeah, you can see it becomes a bit smoother, like a bit more. So you see this. So when it was not there, it was sharp if you remember. But when I added it, it just tends to be a bit smoother. So you see this, all these hyperparameters are extremely important, but there is no way to optimize it. So you have to run a for loop. I'm giving us an exercise. Run a for loop and make sure that which is the best amount out there. And but you will not be able to visualize like I do. So you have to automate the entire process. Does it make sense, guys?
Yes, sir.
Okay. Another important thing is I want to understand is what the dependence on this number of layers. So here the number of layers is, so here the number of layers, where is the layer? Yes, is this 10. So what if we make it 2 and 2? What happens? Let's see. What if we make it 2 and 2? What does it learn? It's not deep, but is it learning something valuable? Let's see. It's pretty good. Just for 2 and 2 layers. Understand this. What if there was only 2 layers? Just instead of this, what if there is, where did it go? Just 2 layers. Like, sorry, 1 layer with 2 neurons. What happens then? Oh, sorry, I didn't change it. I should have changed it here. That's why I was thinking. Why is it not giving good results? I should change it here. Yeah, you see the accuracy has decreased. Now you have to guess why it has decreased. How will the decision boundary look like? Can someone guess? Yes.
I think there would be a lot less lines. Like you just have like maybe 2 or 3 lines instead of the multiple it used to. Yeah, just
Exactly. It's just one line.
yeah, because you only
And
have 2 neurons.
yeah. So let's try to increase it. Let's say we move it to 5, 5. So there are not enough representation power. Okay, now it has improved a bit.
So what if we do like 100 layers with 200 neurons each, just for fun?
Of course, we will do it. So the what issue is that then there will be overfitting issues because it's trying to overfit a lot. We will try to do that. That's a good question. You can see that it's become less, but it's still the curve is coming up. So let's try out what um, Viva, Vivan has said. So let's make it 100, 100, and 100. Oh, the laptop. Okay. Okay, it's giving really less now. Oh, it has written 99.5. See. Well, let's plot a decision boundary. Yeah, it has approximated really well. What if we have more layers, more hundreds? Very
Wait,
good
so
question.
that means
Yes,
5 layers with 100 neurons each, right?
yes. But see,
Okay.
you see, it's not reaching. It's just improving by 1%. You see,
Yeah.
but you see, therefore, this it's becoming less.
Yeah.
Why is that so? Because we are overfitting. And we'll see that.
Yeah. It's taking in apart. It's taking in all the slightly anomalous points.
Exactly. It's taking in the anomalous too. It's 2% less. Yeah, I mean, it's still good. You cannot say it's bad. I think the thing is that this data set is good. That's why. This says it actually has some part, but I mean, it cannot like go bad. The bad thing it can go is okay. So when we are dividing data set, we have some noise. So let's increase the noise. Okay, now it's hard. See. So let's decrease the noise a bit. Yeah, now it's bad. Now it's okay. Let's take this. Yeah, it's running. Let's see. Okay, it's 90.5. Naturally, it will be less because the data set is harder now. But I want more interest in the accuracy. Sorry, the decision boundary. So it's improving. Okay, it's improving a bit. It's reduced. See, this is where the overfitting happens when you move it for a long time. Yeah. So this is the decision boundary. It's not so visible, but let's see that what happens when we have this early stopping now. Oh, see, at 190 it only changes the early stopping. Oh, I think yeah, I think I didn't run it again, or did I? I think I didn't run this again, or what? Yeah. Let's move it to 700 and run it again. Because I think if it stops early, it's a sign of oh, it still stops early. So let's see. This looks still this looks okay because kind of it's symmetric because the dataset is symmetric. So this looks better. It's not overfitting. But if we change this overfitting thing, let's see now what happens. If you remember that was symmetric, it kind of shows the distribution of the moon like this. But what if we don't have that and we run it for long? It has the chance of doing bad, worse. Okay, it's 90, it's reducing. See, the first one was 92, then it's reducing. It reduces again. It started to overfit. You can see the validation loss clearly increases. Okay, it is improved now. It has reduced. So this is something called double descent behavior. This is very important to, like, since you observe this. This is very like visible in neural networks. Okay. Let's see. Yeah, you can see here it's kind of the symmetricness has been lost. It's kind of looking for more red here than there. So we can do it for a few more. Let's say we do it for 2000 epochs. And can we find something? Probably it'll do better. I don't know. It'll keep on doing better. So in the meantime, let's understand the double descent behavior. The double descent behavior is very important property in neural networks where this happens. So if you remember, we said that yesterday we talked about this, if you see on the right hand side, that stop when this happens at the middle, right? That's what we have said yesterday, right? Stop when it started to increase, right? That's what we have said. Stop when it starts to increase. That's the early stopping, right? Yes, right or no? Yes or no? Can you give a thumbs up? Yes. But as you can see here, it first increased and then again dropped. That behavior is called double descent behavior. So it increases. So here it is the classic bias variance trade-off. But at this point of time, what happens is that you have a lot of parameters. So at this point of time, what happens? It's bad because it's interpolation. Like it's very bad. It's like every point is interpolating to each other. But what happens is after this interpolation threshold, there are so many parameters. Now it can play around with it and make it more generalizable. It is modern over parameterized region is makes it more generalizable so that it doesn't just over parameterize. It now decreases the validation loss only. Test error, because it's generalizing with a lot of open parameters. When you are given a lot of freedom, you can do multiple creative things, right? But initially, if you're given a lot of parameters, you will get confused. But as time will pass, you will get more clarity. If you have a lot of things to do, you will understand how to generalize well. That's what exactly is happening here. Okay, so it's beautiful. So let's see what happens here. I have increased. It's okay. It's 1400 now. So okay, it's still not so bad. It's worse than beginning for sure. You can see. So if you remember, there was a increase and then decrease, and it stays constant now. If you see, it's there was an increase and then decrease, and it's staying constant now. The training loss, the validation loss, like around 19 to 20, 0.9 to 0.19 to 0. Okay, now it has decreased suddenly. So this ups and downs are observed many times until it converges, but again it increases. So this is very important to observe it, this loss behavior. But that previous one was a big jump. Okay, so it's trend. Yeah, it's symmetric now. So that's beautiful actually. So it also depends on data set, it not always overfits. It also depends on a data set, how it happens. But yes, I have seen many times, for example, it overfits. Uh, Especially when you have different, so understand we have achieved to this model parameters with various experimentations, 0.01 and all these things. These are not previously done from before. We have experimented and found it out, right, gradually. So which is not always present uh, at your disposal. So you have to previously do it, and then probably that's one of the reasons the model is doing well, even over like in a lot of different places. But overfitting, you have to keep on checking that. The idea to do this is that iterate for, like, do the epochs, train the epochs for a longer time, and take the patience bit to be high. If you take the patience to be high, uh, like for example, what did we do here? We kept it 2000. If I, let's say, keep the patience to be 1000, okay. So and train for longer epochs, then also it kind of removes this whole thing. But again, it's all about, I mean, you are doing it easily over here on a CPU, but it's not always easy to do so many experiments on a Jeep on from large number of data sets. So it's better to enhance intuition and build a strategic pipeline to train the entire thing. If you remember previously at 92 only, it was showing. Oh, I think I didn't turn it on. Sorry. So yeah, let's see. It's 9090, 91. So still it didn't pull the curtain of early stopping because I've kept the patience high. Previously, when I kept the patience 100, it was, you know, flagging me. But you see again, suddenly it dropped. But again, it will decrease. So this double descent behavior happens quite often actually till it converges. I have seen it a lot of times. It's multiple end descent, multiple descents happening. It's an I. It's a good sign that it's learning, according to me. Again, it's a huge jump, but again, you will see the validation accuracy and this loss will decrease, accuracy will increase. See, I'm sure because it's interpolates and then learns, interpolates and then learns. Just like we memorize and then we understand, we memorize and then we understand by practicing. Just like that, it's happening here, and it's happening a lot of times. Okay, it's now really low. It's pretty good. So early stopping didn't raise a flag when you kept enough patience. So if you have enough patience to see it's growing up and down, it's good for you. Yeah, one good thing is to actually see at each point what the loss curve looks like. That's also an important exercise. Yeah, you can see here it's again bad. Okay, so it's early stopped at 1990, 1913. For 1,000 steps, it's kept on increasing. So that's why it's, let's see. Yeah, pretty good. So this is all about it, guys. Any questions? So what you have to do, you go to Kaggle and you can find data sets. Okay, so let me save it. So I have made an entire different code for all the validation and everything. So you can check it out, and I will run it once here. It will take some time though. Just give me a minute. Let me copy the code. So here I will copy the cross validation code, and it'll run for a while. Let's see. Yeah, Nami box. So I've kept it 200. Let's make it 50. Looks good. So in this, all the validation and all this core is there. So let me run it in the meantime. It runs. You can see it runs for multiple folds. Oh, why it's doing 200? I don't know. Yeah, kept it. Oh, here. Let me stop it. Make it 50. Any more 200s? No. So it does the entire thing for you guys, just to check. Yeah. So it runs for all epochs, and You can see that all the folds are running, and so you can see the average is coming out to be this, but here in many of this 96, 95, 93, 92, 94, all these things are coming, but the standard deviation is saying it's robust, it's very low. And then it does hyperparameter tuning for different LR, hidden layer, and dropouts, and finally it will find out the best one. I have written the code for this. Like I have taken the help of ChatGPT. You can see it gives different layers. Yeah, I don't know how many are there, but I hope it ends now. Yes. So you can see the final model. They have found the final model on this. Okay. So after they found the final model, the best model, what they do is that, so remember, you divide the training into training and validation. After you found the best model that you need learning at this one, you need hidden size this one, and you need dropout at this one, it retrains on the entire training data set. Because there's more data, so there will be better results. So and the training data set and got the better accuracy. You can see it's really good accuracy now, 98. And now it evaluates on the test data set. It gets 97%. And you can see the decision boundary here. It's pretty good. And you can see the loss and all. So this is the entire thing you have to do. But yeah, I wanted to come up with your own questions, and I just hope it didn't delete. Yeah, let me save it first. Okay, it's saved. And you go to the data set now. So you can search multivariate classification. And take this. Let's see. Yeah. So you can see that probably you have to predict. So in this case, yes. Let's see. I will. Okay. So I will give you a data set from Kaggle only. So you can make a notebook. So you can make a code, go to code. If I give you a data set, make a code, you can go and create a new notebook for this data set. Okay. As you can see, new notebook, and then do the entire thing. So when you build a new notebook, okay, when you build a new notebook, let's say something like this. Okay, wait, notebooks. Just give me a minute. When you build a new notebook, you will see you will get something like this data set. Okay. You will get something like this data set on the right hand side. A CSV file. So you have to take that CSV file and work with it. But the rest of this is same. Okay. This is all about it, guys. Any questions? I hope you enjoyed it.